What is meteorology? Meteorology is the study of atmospheric phenomena. The root word of meteorology is the Greek word meteorios, which means high in the air. Short-term variations in atmospheric phenomena that interact and affect the environment and life on Earth is called weather. Climate is the long-term average of those variations in weather for a particular area. Remember from chapter 11 that heat is a transfer of thermal energy from warmer to colder materials. Now, I want to contrast weather and climate using the table below. So if I was going to describe weather, I would say that it is atmospheric phenomena interacting. And it is short-term in minutes, hours, days, weeks, or months. Climate, on the other hand, is long-term variations of weather, and it is going to be long-term, and we're talking 30 years or more.
Climate and weather. Together, they are among the most influential forces on Earth. One can influence where and how we choose to live. The other often determines what we do, where we go, and what we wear each day. Climate refers to the average weather conditions of a place over a long period of time. The Earth has 6 main climate zones. Some are mild and inviting, like the Mediterranean climate of southern Europe. Others are harsh, like the arid deserts of northern Africa and the frozen tundra of Greenland. Through history, climate has often played a part in where people have chosen to settle. In the ancient world, some of the first permanent human communities occurred in places with hospitable climates. But humans have long had an amazing capacity to cope with more severe and challenging climates. Today, with widespread use of refrigeration for foods and of air conditioning and heating for homes, humans can survive in all climates, including the frozen desert of Antarctica or the blazing heat of Death Valley, California, where temperatures can soar above 130 degrees. Weather, on the other hand, refers to the day-to-day conditions of the Earth's atmosphere at a particular place and time. Weather can be glorious or annoying. It can also be devastating. Severe weather can destroy homes and property, cripple transportation, ruin crops, and create havoc for people caught in its path. In the United States, weather causes, on average, more than $11.4 billion in damages each year. About 15% of that damage occurs in Florida alone, a state that sees more than its share of hurricanes, floods, and tornadoes. An accurate weather forecast can make it possible for people to prepare for severe conditions before they strike. In cases of hurricanes, tornadoes, and floods, a warning can save lives by giving people time to get out of harm's way. With so much at stake, atmospheric scientists, called meteorologists, are working with new technologies to find better ways to forecast the weather. Powerful computers process atmospheric information to create weather maps and models. Radars track storms on the move and can detect rain up to 250 miles away. Weather satellites look down on the Earth from space, monitoring everything from cloud cover and precipitation to lightning strikes and fluctuations in the temperature of the oceans. There are even research planes that fly into hurricanes to help scientists learn about the inner workings of some of the planet's deadliest storms. In some cases, the study of meteorology can be a nail-biting adventure, as scientists risk their lives to study tornadoes and other dangerous weather phenomena. As scientists continue to study weather patterns and behavior, we can expect to find more ways to predict its course. And the next time severe weather strikes, perhaps we'll be ready.
Air masses.
An air mass is a huge body of air, so large that it often stretches for several thousand miles. Air masses generally have similar temperature and moisture properties throughout. The geographical location from which an air mass originates is its source. The types of air masses formed on Earth are determined by their source region.
Air masses can have one of 4 qualities: continental, maritime, tropical, or polar.
Continental air masses occur over large land masses and usually contain less moisture than other air masses, meaning they tend to be dry. Maritime air masses originate over a large body of water and are also known as oceanic air masses. Because they form over water, they are moist. Tropical air masses form in regions of lower latitudes and are usually warm. Polar air masses form over polar ice caps and are very cold. As these air masses move across Earth's surface, they will change, becoming modified according to the characteristics of the location beneath them. For example, an Arctic air mass with very cold and dry air moving across the ocean will become warm and moist, changing over to a moist maritime polar air mass. When this polar air mass moves south from Canada into the southern United States, it will acquire warmth from the ground below and become drier due to a lack of moisture. This air mass has now become a continental polar air mass. When air masses stay long over a region, they control the weather of those regions.
And over continents like this, we find air masses that are relatively dry. Several major air masses affect our weather in the United States. Maritime tropical air masses, forming over the oceans near the equator, are warm with a great deal of moisture. During the summer, these air masses usually result in rain. But in the colder months, the precipitation could be snow.
In the northern Pacific Ocean and in the North Atlantic, we sometimes find maritime polar air masses. During the summer, these air masses in the Pacific usually mean fog along the west coast. In the east, they often result in cooler temperatures. But in the winter, these polar masses from the oceans can produce heavy snow and sometimes even blizzards. To the south, continental tropical air masses form over Mexico during the summer, bringing hot, dry air to many states in the United States Southwest. Finally, continental polar air masses form over northern Canada, resulting in very cold winter temperatures in parts.
An air mass is a large volume of air that has the same characteristics such as humidity and temperature as its source region. A source region is the area over which the air mass forms. Now, if you look at this diagram, you can see that the Arctic and polar air masses are up in the northern hemisphere, and the maritime and tropical are down closer to the equator. The continental polar comes from the northern part of the northern hemisphere over the continent of North America, and the continental tropical air mass that you see on the bottom of the United States comes from Mexico. Number 1, compare and contrast the source regions of continental and maritime air masses. That's what I just did. Continental air masses originate over land, maritime air masses originate over water. How did the source regions of polar and tropical air masses differ? I also just explained that. Polar air masses originate over cold polar areas, and tropical air masses originate over warm tropical areas. Which air masses influence the northwestern United States, and what type of weather do these bring? Well, if I'm looking at the northwestern United States, that's along the west coast, and I see two things happening. The maritime Pacific air masses influence weather. They bring cool and humid weather. So if you look at the maritime polar, which is coming off of the Pacific Ocean into, let's say, Washington or Oregon, they're going to be cool and humid. Number 4, which type of air mass brings cold, dry weather to the northeastern United States? So I'm looking for cold and dry. Cold and dry has got to come from the polar continental air masses. Continental polar, which is going to bring cold and dry, because remember, when it occurs over land, it's going to be a dry air mass. When it occurs over the sea, it's going to be a humid air mass. And also remember that you're going to get cold airs from the Arctic area, and you're going to get warm air from the maritime or tropical area. Explain why cool, dry summer weather in the central United States might change to hot, dry weather. While I'm looking here, if the continental tropical air mass starts to move into the central United States, what's going to happen is it's going to replace that cool, dry summer with hot, dry summer. So the continental polar air mass moves over the area, which gets replaced by the continental tropical air mass, which is shown to bring dry and hot weather. Number 6, compare and contrast the influence of maritime polar and maritime tropical air masses. So when I look at the map, they're both maritime air masses, so they're both going to bring humid weather. However, the maritime polar air mass is going to bring cool, while the maritime tropical is going to bring warm. What change would air mass modification cause in a continental polar air mass that moves south over the central United States? The air mass would warm up as it moves south over the warmer land surfaces. Now, I want to talk about the different types of air masses, their sources, and their weather associated. This is a great table to study when you're talking about air mass movement. So we're going to start with the first blank, which is the continental tropical, because on the right, it tells you weather associated with this air mass is hot and dry. So if it's going to be hot, that's going to mean it's tropical. If it's going to be dry, that means it's going to be over a continent. Because remember, you get moisture from maritime, you get dry from continental. Now, the source of that air mass for the continental tropical would be the deserts of the Southwest and Mexico. Now, a maritime tropical is going to come from the tropical and subtropical oceans, and the weather associated with maritime tropical is always going to be hot and humid. Now, which one comes from the interior of Canada and Alaska? That would be a continental polar because it's in the northern part, and the type of weather you get from a continental polar is cold, cold winters and cool, dry summers. The last that we'd like to talk about is heavy rains in the winter on the west coast. Well, those are coming from maritime polar. And the sources are the cold waters of the North Atlantic and the North Pacific. Now, for the west coast, it's going to be the Pacific, and for the east coast, if we were talking about that, it would be the North Atlantic. And last but not least, the Arctic comes from the latitudes over 60 degrees north. So anything above 60 degrees north is going to be considered Arctic, and that is going to be extreme cold. What if you're visiting the deserts of the southwestern United States? So we're talking Arizona, Nevada. A sudden thunderstorm moves in. Hypothesize what type of air mass could have brought that storm and where it originated. Well, if it's a thunderstorm, that's going to be a moist air mass. So my thought would be it would come from a maritime tropical air mass from the Pacific Ocean, because you're in the southwest, so that's going to be maritime, and it's going to have to be tropical also because you're in the southwest part of the United States. Section 2, weather systems. The directions of Earth winds are influenced by its rotation. The Coriolis effect results in fluids and objects moving in an apparent curved path rather than a straight line. So we have several listed in this diagram. We have the polar easterlies, we have the prevailing westerlies, the horse latitudes, the northern trades, the southeast trades, and the prevailing west and the polar easts. Now, when you talk about wind direction, you're always, when you say it's an easterly, it's coming from the east. Same thing with a westerly, comes from the west. So when you're talking about wind direction, it's its source. The Coriolis effect results in fluids moving in an apparent curved path rather than a straight line. Now, I've said that before, so let me show you what it looks like.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
So, we have global wind systems. The direction of Earth's wind systems, such as the polar easterlies and trade winds, vary with the latitudes in which they occur. Now, the polar easterlies, boom. They're the wind zones between 60 degrees north latitude and the North Pole and 60 degrees south latitude and the South Pole. And they're called the polar easterlies because they're in the polar region and they come from the east. The prevailing westerlies are the wind systems located between 30 degrees and 60 degrees north and 30 degrees and 60 degrees south. Now, we are in the northern prevailing westerly because we're in the northern hemisphere and we are between 30 and 60 degrees. Now, you'll notice the westerlies come from the west, go to the east. The trade winds between 30 degrees north and 30 degrees south are two circulation belts of wind known as the trade winds, and both of them come from the east and go to the west. Near latitudes 30 degrees north and 30 degrees south, the sinking air associated with the trade winds creates an area of high pressure. This results in a belt of weak surface winds called the horse latitudes. Now, according to legend, the term horse latitude comes from ships that were sailing to the New World and they would be stalled for days or weeks when they encountered areas of high pressure and calm winds. Many of these ships also carried horses as part of their cargo. Unable to sail and resupply due to lack of wind, crews often ran out of drinking water. To conserve the water, the sailors of these ships would sometimes throw the horses they were transporting overboard. Thus, the phrase horse latitudes was born. Trade winds. Trade winds from the north and south meet and join near the equator. The air is forced upward, which creates an area of low pressure. This process is called convergence, and this can occur on small or large scale near the equator. It occurs over a large area called the Intertropical Convergence Zone, or the ITCZ. A large temperature gradient in the upper level air combined with the Coriolis effect results in strong westerly winds called jet streams. A jet stream is a narrow band of fast high-altitude westerly wind. Weather in the middle latitudes is strongly influenced by these fast-moving high-altitude jet streams. The major jet streams, called polar jet streams, separate the polar easterlies from the prevailing westerlies. A minor jet stream, known as the subtropical jet streams, occur where the trade winds meet the prevailing westerlies. Jet streams in our weather. Storms form along jet streams and can generate large-scale weather systems. Jet streams affect the intensity of weather by moving air of different temperatures from one region to another. So you're seeing here, the jet stream air is moving. So when it's coming from the north, you're going to get cold air. And what would happen is if it then the warm air forces it north, then you would get warm air. But the jet stream will then affect our weather. What would happen to the weather in the northeastern United States if the polar jet stream dipped to the south, like you're seeing here? How would the weather change if it moved to the north? So let's see this dip again. It's dipping, the cold air is coming down, and then later the warm air pushes it back up.
Huge air masses can be found all across our Earth. An air mass is a large area of air which has a similar temperature and humidity throughout. Fronts are the invisible boundaries that occur between two air masses. Based on the temperature of an air mass, a front can be either cold or warm.
The masses don't mix, but instead one mass pushes the other along. This boundary is called a front. A cold front forms when a cold air mass pushes a warm air mass. Because the cold air is denser than the warm air is pushed up quickly. As the warm air rises quickly, the moisture in the warm air cools and condenses. The water vapor changes to tiny drops of liquid water. Clouds form as a result of this cooling. The clouds that form are usually cumulus clouds. The size of the clouds depend on the amount of moisture present in the warm air mass. Precipitation is often heavy along a cold front. It may not last long, but it is generally a heavy rain with increased wind speed. Thunderstorms are common along cold fronts. During the winter, snowstorms and blizzards may occur along a cold front, depending on the temperature differential and the amount of available moisture.
Cold fronts are represented as blue lines with triangles pointing in the direction the front is moving. Cold fronts move from the northwest to the southeast. When a cold front passes over an area, temperatures may drop as much as 15 degrees, sometimes even more than that. As they're moving, air masses don't mix. Instead, one will push the other. Cold fronts move faster than warm fronts.
Cold air is denser than warm air, causing cold air masses to be harder to remove from the Earth's surface. So when cold and warm air masses meet, the cold front will move beneath the warm air, lifting it upwards.
The incoming cold front will create a sudden drop in temperature along with heavy rain and sometimes even hail, thunder, and lightning. The lifted warm air will produce clouds and thunderstorms.
A warm front occurs when a warm air mass pushes a cold air mass. The warm air moves up and over the cold front. Notice that the movement of the warm air over the cold is at a much more gradual slope than at a cold front. The warm air does not rise as fast as it does in a cold front, so the clouds that form are different. They are thinner and spread out over a greater area. These clouds are called stratus. These high clouds are a sign that a warm front is approaching. A warm front moves through an area much slower than a cold front. The clouds associated with warm fronts are thick, low clouds that produce a steady, light rain. This may last for a day or more.
A warm front is the border at the forward edge of a warmer air mass that is pushing a cold air mass. On weather maps, warm fronts are illustrated using red lines with semicircles on them. When this warm air pushes the cold air, the warm air will slide across the cold front. Compared with the cold air, the warm air will move much slower and form thin stratus clouds, which may cause drizzles.
Sometimes the boundary between a cold and warm air mass doesn't move. In that case, it is referred to as a stationary front.
A stationary front often produces overcast weather and drizzles that last for several days. Stationary fronts are represented as alternating red and blue lines with blue triangles pointing towards the warmer air and red semicircles pointing towards the colder air.
Sometimes when a cold front is overtaking a warm front, the warm front is actually lifted above the ground. This may create drastic temperature changes and violent weather. This type of rare front is called an occluded front.
A collision of two air masses forms a front, a narrow region between two air masses that have different densities. Now remember, warm air has a lower density than cold air. So if I'm looking at a weather map and I see a cold front, the symbol I'm going to see is going to be a line with triangles pointing toward the direction that the cold front's moving. If it's a warm front, I will see a line with semicircles showing that the direction that it is moving. A stationary front shows both, but it always shows the direction you can tell which each came from. An occluded front shows both, but they're pointing in the same direction because they are actually stopping each other. Now, the air movement in a cold front, cold air displaces warm air, forces the warm air up, and it does that quickly. And warm air displacing cold air happens in a warm front. So basically, the thing that is doing the moving is what the front is called. So if the cold air is moving the warm, that's called a cold front. If the warm air is moving the cold, that's called a warm front. A stationary is when two air masses meet, but they kind of just butt heads. They don't advance. So they're not moving. Stationary means staying still. And then last but not least, a occluded front is when you get fast cold air wedging warm air up where it gets trapped between the two cold air masses. And that is the worst one when it comes to weather. Cold fronts usually will give you clouds, showers, thunderstorms. Warm fronts, very cloudy, precipitation. Stationary, somewhat cloudy, light precipitation. And occluded is definitely precipitation. That's when you get some of your worst storms. Sinking or rising air combined with the Coriolis effect results in the formation of rotating high and low pressure systems. A low pressure system is, in surface low pressure system, the air is rising. When air from the outside replaces the rising air, it spirals inward towards the center and then upward. High pressure system is a system where you have sinking air moving away from the center when it reaches the Earth's surface. So low pressure systems are moving toward each other, high pressure systems are moving away from each other. Now, both low pressure and high pressure systems are formed by internal forces, and the air will always move in a circular motion. Low pressure systems, the winds move counterclockwise, there's rising air and stormy weather. Where on the other hand, high pressure systems, the winds move clockwise in the northern hemisphere, sinking air and fair weather. In the northern hemisphere, winds move counterclockwise around a low pressure system and clockwise around a high pressure system. Let's let Scott tell you more.
Why is high pressure associated with clear skies and light winds, and low pressure associated with storms and rain? Well, we're going to put it together this way. You have to look at weather as three-dimensional. That's the key here. That was one of the most difficult things when I went to college. When they started talking about the weather in 3 dimensions, I was so used to just staring at weather maps that I'd see in the newspaper here down at the ground. But everything at the ground is occurring by what's happening aloft here. So let's look at the jet stream. This is the jet stream here. This is high and low pressure here. Now you have to understand the water cycle too. The water cycle is as air rises, it will cool and then condense because it encounters lower pressure. So the higher air rises, the pressure goes from high pressure to low pressure. You have less pressure, less temperature, it cools and condenses, makes clouds. So wherever there's rising air, we get precipitation. This is what's happening in the jet stream aloft. Here we'll have a convergence zone aloft here. That's when the jet stream winds are coming together. So as you push the air together, it has nowhere else to go. It can't go up, so it has to go down. And so what happens is we have sinking air, and the air sinks, and it sinks clockwise. So it subsides, as we call it, subsides. As it's sinking, it warms because it encounters the higher pressure near the ground, and that sinking air also causes a big bubble of high pressure to form here. So sinking air near the high pressure warms and dries, and so you don't have any cloud cover out. We had that pretty much during the day today. As the jet stream is going along, it'll encounter an area where it diverges aloft, and so it separates the air here. We can't have a void. We can't make a vacuum with no air, so something has to replace the air right here, and so air comes up from the ground. So what happens is high pressure now has been over here, so that wind comes out of high pressure, it goes into low pressure counterclockwise, it gets to the middle with nowhere else to go, and it rises to fill this void right here. And so near low pressure we have rising air, and rising air will then cool and condense and make clouds and precipitation. So you basically have rising air causing clouds and rain, while sinking air is generally dry as it warms up. And if you look at high pressure, low pressure on the ground at the surface here, you also have wind that forms between the two. And as I mentioned to the kids, if I take a room and we fill it up with air, we seal it off, and we pump a bunch of air pressure inside the room, then we open the door, the air will rush from high pressure to low pressure outside the door, and because the earth is spinning, it goes around clockwise like this. And so we added a little bit extra here, but generally stormy.
So as he was saying, when you have rising air in a low pressure system, that's going to cause a low pressure center. When you have subsiding air or air coming down, that's going to be a high pressure center. So you can always remember low pressure is going to deal with more rain and precipitation, where high pressure, since it is now pressing the water down, it can no longer condense, and it actually will cause it to go back into the gaseous form, which is no clouds. I'm going to stop there.